This is the fourth lecture on rigid body dynamics. In the earlier class, we have obtained a relation between linear and angular kinetics. That is, we obtained that displacement of the ith particle when the rigid body as a whole is rotated by an angle theta, d theta is governed by this. The velocity of the ith particle uh, is given by omega n cross Ri, and acceleration is given by uh, alpha n cross Ri plus omega square Ri. So this relation holds when the rotation takes place around an axis characterized by n cap. For rotation about a fixed axis, n cap is a constant vector, constant unit vector, and for rotation about a point of a rigid body, n cap changes continuously. So this is the rotation about for about n cap. And if we assume the rotation about the z-axis of Cartesian coordinate system, in the earlier class we have obtained the relation both in Cartesian and cylindrical coordinates. But here we shall, since we shall consider the angular momentum and torque, these are best represented in Cartesian coordinate system. So we will confine ourselves to Cartesian system, in which case dr becomes minus I cap yi j cap xi d theta, vi becomes omega minus I cap yi j cap xi, and acceleration A is minus I cap alpha yi plus omega square xi plus j cap alpha xi minus omega square yi. These are the relations that we have obtained in the earlier class. Now with this introduction, we shall consider the rotation of a rigid body about a fixed axis. So we consider let me rewrite this. Rotation of a rigid body about a fixed axis. Say this, the direction of the axis of rotation is characterized by n cap. Actually, consider a rigid body. This is a rigid body, and we have 2 points when it is fixed. So we consider an axis or straight line passing through these 2 fixed points. Say O and O prime are the 2 fixed points, and the ball, this direction is called the n cap direction. The axis is the direction of the axis is specified by them. And if we choose O as the origin, and then we have a point Ri, mass Mi, its position vector is Ri with respect to this, and this particle executes a circular motion whose center lies on the axis of rotation. This is O prime, and this much is the rho I is equal to n cap cross Ri magnitude. This is the picture that we shall refer to in the derivation. So first thing that we are interested is the angular momentum. Momentum of the rigid body when it is executing a rotation about a fixed axis. So the angular momentum L is the sum of angular momentum. So this is the sum over Li, and for Li we write it as Ri times Mi Vi. So this is summation over I Mi Ri cross V, and for V we write this relation. This is cross omega n cap cross Ri. So which comes out to be summation over I. Omega is the same for all the particles of the rigid body, so we take omega out of the summation sign, and the rest part becomes n cap Ri square Ri times n cap Ri. This is the general expression for angular momentum. If we take the component of the angular momentum in the direction of axis of rotation, so component of L along n cap, this is denoted by Ln is equal to vector L times n cap. So we see when we dotted it what n cap, this is simply Ri square, and this much is Ri dot n whole square. This is Ri dot n is the component of Ri in the direction of this. So this much O prime is this. So this part is actually rho I square. So this is omega summation over I Mi rho I square. This is the moment of inertia. So we call it omega In, where In is equal to summation over I Mi rho I square. If we assume that the rotation are taking place about z axis, so this is equal to, this reduces to Iz z is equal to summation over I xi square plus yi square for rotation about z axis. In general, we see that L is not in the direction of omega. When a body executes circular motion, the direction of omega is along the direction of n cap, that is omega is in general written as n cap omega, that we have discussed in the earlier class. We see that L is not in the direction of n cap entirely, it has other components. So in general we can write in Cartesian space, in xyz space, this can be written as L is equal to omega summation over I mi. This is n cap, that is we consider the rotation to be taking place along z axis. So this is k cap ri square minus ri, and this is simply zi, wherein we have chosen that but n cap is equal to k cap, so that in this part is simply zi. So if we rewrite it, we get this. There is a contribution to I direction. This is xi times zi. Similarly, there is a contribution along y direction, which is yi times zi. For the z direction, this is zi square, which cancels with this, and we define k cap xi square yi square. This is written as omega times I cap I xz plus j cap I yz plus k cap I zz, where the moment of inertia and the product moment of inertia are defined like this. I xz is equal to summation over I mi. The product moment of inertia are defined as I xz is equal to minus summation over I mi xi zi, which is obviously equal to Izx. Iyz is defined as summation over I mi yizi. This is obviously equal to I zy, and Iyy was defined earlier. Sorry, Izz was defined earlier. These are the moment of inertia and product moment of inertia. We can in general define I alpha beta is equal to summation over I mi ri square delta alpha beta minus xi alpha xi beta, where we have used the notation that is xi1 is equal to xi, xi2 is equal to yi, xi3 is equal to zi, this notation. So this is the moment of inertia. We see from this expression, we see that L is not in the direction of omega, because omega is along k cap. So L is not in general in the the direction of omega that we have obtained in linear dynamics. However, for a symmetric body, if the axis of rotation be an axis of symmetry, then this product moment of inertia vanishes, and in which case L becomes parallel to omega. Otherwise, if so, for rotation about a symmetric axis, L is parallel to omega. So we write in general for rotation about rotation about z-axis, we have L is equal to omega I cap x z plus j cap I y z plus k cap I z z. Or if z-axis be a axis of symmetry, if z-axis be an axis of symmetry, then I x z is equal to 0 is equal to I y z. Because the mass points are distributed symmetrically about z-axis, so for a given combination of x, y, it is equally likely to have positive value of z as well as the same negative value of z with the same magnitude, so which cancels this. And in which case this becomes L is equal to omega I z z k cap, which can be written as I z z omega. So this is a vector relation. So in which case the momentum inertia, it is a scalar, but it is not a vector relation, as we shall explain afterwards. So the lesson is that the angular momentum L is in general can be written as I cap I x z plus j cap I y z plus k cap I z z multiplied by omega. This is the angular momentum. And if we consider rotation about x axis, then Ln is equal to In omega. This is in the component form. We consider another quantity which is of importance is the torque, which is defined as the moment of force. It is the moment of force. If we consider the motion of a rigid body about a point O, then torque about O. This is N is equal to summation over Ni. This is defined as summation over I, Ri cross Fi. The internal forces do not take place, do not contribute, so we write it as summation over Mi Ri cross Ai. For rotation about n cap, we know the expression for Ai, so this becomes summation over Mi Ri cross, this is alpha n cross Ri plus omega square this is alpha times, first term is n cap dot ri square. This is this contribution minus n cap dot ri times ri, and if you cross this, there is two contribution, one is from there, other one is from there, which is 0. So we write omega square n dot ri times ri cross n. This is the general expression for the torque. If we take the component of torque in the direction of axis of rotation, which is defined as n times n cap, so the contribution comes from here, summation over I, mi. This is n dot n is 1, so this is alpha ri square, and this is dotted with n cap, so this is n cap dot ri square, and if we dot it, cross it with this, the vector term becomes becomes ri cross ri dot n, which is 0. Sorry, when we take the dot product of this is 0. So these terms do not contribute. So this is the component of torque in the direction of axis of rotation. Obviously, this part is so alpha is multiplied all along. Alpha is multiplied all along, and since alpha is the same for all the particles of the rigid body, we take it out of this, and this part is simply rho I square. So we write it is alpha in. Which can be written as ddt of in omega, where omega in is constant, so we can write it as ddt of ln, or this can be written as ddt of L times n cap. So we see that whenever we are considering the axis, a rotation of a rigid body about an axis, fixed axis, the vector relation are valid in terms of the components. So to say, we see that in for torque we have in n is equal to alpha in is equal to ddt of ln. And in general, the torque has a complicated expression which can be better worked out in Cartesian coordinates. In general, the torque expression is, in general, for rotation about z axis, we have n. We use this expression. So this is summation over I. Mi alpha is taken common, so this is k cap ri square. This is minus zi square, because we are considering the rotation this part is zi and this is r, and this part is plus omega square, this part is simply zi, and this cross product is I cap yi minus j cap xi. we collect the component, we have summation over mi, summation over mi. There is a contribution to I cap from here, so this is I cap minus xi minus alpha xi zi, and here is a contribution to I cap, this is omega square yi zi plus contribution to j cap, this contribution is minus alpha yi zi, and here is a contribution minus omega square xi zi, and the k cap contribution comes from there, this is plus k cap alpha, this is xi square plus y square plus zi square, and there is a cancellation from zi there, so this is simply xi square yi square. So if we collect the term and write it in terms of moment of inertia, this becomes I cap, this part is alpha ix jet, this is omega square minus omega square Iyz plus j cap alpha Iyz plus omega square Ix jet, and this is k cap alpha Izz. This is the expression for the torque. So we see in general torque is not in the direction of angular momentum, because the angular momentum and the relation between torque and angular momentum is a complicated one. Now, but the vector relation between angular quantities do hold in the form that we are habituated with, in the form of their components when taken in the direction of axis of rotation. Now we shall consider two scalar quantities which are very relevant in connection with rotation of a rigid body. Namely, we shall consider the rotational kinetic energy and the work done in rotating a rigid body. So first I come to the kinetic energy of a rigid body. Kinetic energy or rotational kinetic energy. Rotational kinetic energy of a rigid body executing rotation about a fixed axis. So the kinetic energy Tr is sum over half mi vi square dot vi, which if we write it like this, Ri square. So this omega cross Ri, what we write it as half, or sorry, we write this term as this half summation over mi. This is bi cross, this bi is written as omega cross Ri, as bi is for rotation This is Vi is equal to omega cross Ri. So this is a scalar triple product which can be written as omega taken out. So this is half summation over mi omega dot Ri cross Vi sum over I. Here we have made two interchanges, firstly with omega and V and secondly with V but R, so the sign remains unchanged, and we take omega out in the dot mode and the rest of the quantity is summation over mi Ri cross Vi. This is nothing but the angular momentum of the rigid body. So this is half omega dot L. This is the relation between angular momentum. This is the relation of rotational kinetic energy. If we write L in terms of its component, and if we write it as half omega dot L, for L we write this one, it is omega times I cap, omega times I cap I x jet plus j cap I y z plus I cap k z z, and omega is written as k cap omega, then this simply becomes half I z z omega square. The analogous relation of in linear dynamics of is the kinetic energy T is equal to half mv square. So the role of mass is being played by the moment of inertia and linear velocity is replaced by angular velocity. So the scalar quantities, for scalar quantities, you need not to take components, it is valid in its original form. Now, the last thing that we shall consider is the work done in rotating a rigid body by an amount theta. Work done in rotating a rigid body by d theta about an axis of rotation n cap. So we consider the rotation of a rigid body about a fixed axis and what is the work done required to do in displacing the rigid body. The work, we start with the definition that dW is equal to summation over I Fi dot Ri. For Fi we write it is mi times acceleration, and for Ri we write this expression n cap cos Ri times theta. And the expression for E is summation over I mi. For E it is alpha n cap dot Ri plus omega square Ri square, and this is being dotted with n dot Ri d theta. We first consider the contribution of this term. So this is summation over I, mi, this is alpha times n cap dot Ri magnitude square. And if we consider the dot product of this, n cap dot n cap cross Ri is 0, so n cap dot Ri is 0, and if we consider this part, this is the vector Ri. This is vector Ri, and then we have for the second term Ri dot n cross Ri. This is also 0, so this term do not contribute, and this is d theta. So that we get this is alpha I and d theta. This is the wall. Now you recall that this much is the top, nth component of top. So this resembles the relation that W is equal to f dx. So this relation holds for angular dynamics for the rotation of a rigid body along a fixed axis. In the next class, we shall consider an example on this, and we shall consider a more general motion of a rigid body where a rigid body is rotating about an axis whose direction is fixed, but the axis as a whole is in motion.